Hello and welcome. My name is Maciej Soja, and in this video I will talk about radar measurements of forests. Many remote sensing techniques rely on measurements in the visible or infrared regions of the electromagnetic spectrum. This is often problematic because in these regions clouds absorb and scatter electromagnetic radiation and thus obscure the ground. Clouds are therefore one of the biggest problems with optical sensors. Clouds are virtually transparent to electromagnetic waves with frequencies in the approximate interval 30 MHz to 10 GHz. The region between these frequencies is often called the radio window. The radio window is used by radar systems. Radar stands for radio detection and ranging. Radar systems transmit radio or microwave frequency pulses, usually within the radio window, and they analyze the reflected signal to acquire information about the surroundings. Radar is similar to echolocation, which is an ultrasonic technique used by bats and toothed whales in optically dense environments. The radio window is traditionally split into several radar bands for easier classification of radar systems and easier referencing to the used frequency. Synthetic aperture radar, SAR, is a high-resolution imaging radar system. In SAR, the radar antenna is mounted on a moving platform, side-looking and pointing towards the ground. The system scans the ground by sending multiple pulses as the platform moves along the flight track. High range resolution is obtained by transmitting a coded wideband signal. High azimuth resolution is obtained using coherent processing. It uses the fact that the same target on the ground is covered by multiple consequent acquisitions. The exact position of the target can be determined from the measured Doppler shift. This way, a larger synthetic aperture antenna can be created, giving a better azimuth resolution. Electromagnetic waves scatter strongest from objects larger or comparable in size to the wavelength. This means that in forest, longer waves see deeper into the canopy because trees usually have the smallest elements in the top and the largest elements near the ground. For boreal forests, foliage penetrating capabilities are observed already at P-band with wavelengths around 80 centimeters. Another consequence of the coupling between wavelength and scatterer size is that surfaces which appear rough at one frequency may appear smooth at lower frequencies, because the roughness becomes smaller in comparison to the wavelength. Let's now have a quick look at what this implies from forests. For short waves, typically X and C bands with wavelengths of a few centimeters, most scattering occurs in the top of the canopy, from leaves, needles, and branches facing the radar system, and from the rough ground. For longer waves, typically with wavelengths of a few decimeters, most scattering occurs within the canopy from larger branches facing the radar system. Also, some double bounce interactions between the trunk and ground, which now may appear smooth, is possible. Direct reflection from the ground decreases due to its increased smoothness. For much longer wavelengths, typically around a few meters, the double bounce interaction between the now smooth ground and trunk becomes the strongest effect. Scattering strength also depends on the properties of the material of which the target is made. Metals and water scatter very strongly, whereas plastics and dry soil scatter very weakly. Due to the side-looking geometry of SAR systems, geometric effects may be present in radar images. For example, elevated objects will typically appear closer to the radar. Just like optical images, radar images have shadows in regions where radar illumination is obscured by strongly scattering objects. Since coherent signals are used in radar imaging, interference between scatterers within a resolution cell may occur. This gives rise to an effect called speckle, which produces a noise-like pattern in radar images. Now let's have a look at some real SAR images and see the effects that we talked about. When the wavelength is around 3 centimeters, Earth's surface may look like this. We can see that the lakes appear very dark, their surfaces are smooth, and the reflection towards the radar is weak. We can see some shadows and some strong scattering when the radar is facing this forest edge. A very strong reflection is observed from a corner reflector, which is a calibration target made to give a strong backscatter. The grainy pattern over the entire image is speckle, the coherent noise-like effect due to interference between scatterers within a resolution cell. At P-band, when the wavelength is around 80 centimeters, the ground appears different. Low backscatter is observed from fields which appear smooth at these wavelengths. We can see structures in the forest which we couldn't see before because P-band penetrates through the canopy and uncovers sub-canopy structures. Also at P-band, the corner reflector appears strong. This figure shows the sensitivity to biomass. To the left, we can see a reference biomass map. In the center and to the right, we can see 5 SAR images of the same region from similar geometries, but acquired at decreasing wavelengths. For the longest waves, the same structures in the forest can be observed as in the biomass map. For the shorter waves, the biomass map and the SAR images are completely different, hinting that shorter waves do not have the capability to measure biomass. Summarizing, synthetic aperture radar provides weather and daylight-independent, high-resolution imagery. Radar systems can be trimmed to fit certain needs, primarily through the choice of frequency. Long-wave SAR systems, typically with wavelengths above several decimeters, show good sensitivity to biomass. Currently, the most difficult task related to radar imaging of forests is the interpretation of radar images, as our eyes are not used to seeing the world with such long waves. Thank you for watching and goodbye.